Hello everyone. In this video, we are going to solve a problem from dynamics for particles, and it is going to be solved using the principle of work energy. So in this problem, we have two objects, A and B, where object B is 135 kilogram and object A is 90 kilogram. And they are connected by a rope which is passed over a pulley, and object A is going to move along the vertical guide, which is smooth, meaning that there is no kinetic friction, and it is also attached to the spring at the bottom, which is initially compressed. It doesn't say how much the compression is, it just says initially it is compressed. Now you release the system from rest, and when object B falls for 1 meter, you want to know the velocity for each one of these objects. Okay, so let's start. So again, this guy here, this one is smooth, which means no friction. So, first of all, in this case, the velocities of the two particles A and B are not the same, although they are connected by a rope that cannot be stretched, but it doesn't mean the velocities are the same. And the main reason here is this angle here, if you call this angle alpha. Because of this angle alpha, the two velocities are not going to be the same. If this angle was 0 and A was also hanging from the rope like B is just over the pulley without this angle alpha, then yes, you can assume they are the same, they have the same speed, but not here. And I'll show you why. So here I'm going to draw this system which involves A, the rope, and B. I'm going to draw it first in the beginning and then when B falls for 1 meter. Okay? And then we are going to compare and we are going to draw several equations from there. So situation 1, this is A, this is the rope, and this is B. So I show situation 1 with color blue, then situation 2, B drops for 1 meter. So let's say B comes here. A goes up. So A has to stay along this vertical guide, this distance of 2 meters, this distance is not going to change. So A is going to be like somewhere here. And so the angle of the rope has to change. It goes like that. Okay, the length of the rope in both situations has to stay the same because it cannot be stretched. So here, this is the displacement of block B, right? I can call it whatever you want, delta y of block B, which is equal to 1 meter. This is the displacement of block A. This is delta y of A, which is not given, and we have to find it. And here, we know this distance between the rope of object B and the guide that A moves along, this distance here, is going to stay at constant of 2 meters. And I also consider the initial length of the rope from the pulley to B, this distance, to be some distance like D. Okay? Also, based on what I did here, it's better to draw the top of the B to the top of the next situation. This one, call it delta Y. Would be a little bit cleaner if you use it this way. So right now, if I ask you what is the length of the rope in situation 1, L1, the length of the rope, how much is it? You'll say it is equal to D plus some distance over the pulley, right? Your D can even include that if you want, or you can call that another distance, right? So maybe this one you can call D1, and then some small distance that is along the, it's over the pulley, you can call that D2. So it is D1 plus D2, right? And then this diagonal, which was a 2 meter and a 3 meter hypotenuse of that, so it is going to be the square root of 2 squared plus 3 squared. This is the length of the rope in situation 1. It is equal to the length of the rope in situation 2, which is how much? So in situation 2, the length of the rope on the right hand side is D1 plus delta Y of B plus the constant of D2. Now D2 can change a little bit, but not significantly due to the change in the angle. And then you have this hypotenuse, which is what? Here, this is the hypotenuse of a triangle like that, where this side of it is 2 and this side is going to be whatever it was in the beginning, which was 3, but now delta Y of A is gone, so it is 3 minus delta Y of A, right? The hypotenuse of that triangle is going to be the new length on the left hand side. So this is what you have. And again, they have to be equal. So the D1 and D2, you can get rid of them on the two sides. And from here, you can see that this is going to be square root 13, right? And you'll see that your delta Y of B, correct? If you bring it to the left-hand side, minus delta Y of B plus square root 13 is equal to square root of, and if you square that number and simplify it, right, or you can keep it as is. Let me just keep it as is for the moment, because when we want to solve something, that's going to be easier to use it as is. So this is what you have. Okay, this is your equation between YA and YB. Clearly, it's not a linear relation. Now, if I plug in 1 in here, the question is how much is delta Y of A? Well, we can solve, right? So all we need is to square this left-hand side, square the right-hand side. It gives us a number. We take the 4 to the left-hand side, take a square root, and that gives us this guy. And then by switching the left and right-hand side, I can get delta Y of A, correct? So from here, clearly you see that delta Y of A is going to be 1.33 meters. So B goes down 1 meter, but A goes up 1.33. Okay, so A has to go up more, and that is clear because of the angle. Okay. Okay, so clearly A does move differently than B. Clearly, you see that the amount of displacement in the same time is different. But also what I can do from this equation that I just derived for relation between delta YA and delta YB, I can also take a time derivative from this equation. So I'm going to take a time derivative from this equation, or divide it by delta t and then let delta t go to 0. And why do I do that? Because it gives me a relation between the velocities of A and B. If you pay attention to the problem, it says what are the velocities? So I need to find velocity of A and velocity of B, and you know the work energy equation, when I write it for the entire system, it only gives me one equation, and if I know everything else in that equation, I still have two velocities unknown in it, VA and VB, when they show up in the kinetic energy. So if I want to solve for both, I need to know how those two are related to each other, so that instead of two unknowns in that work energy equation, I will end up with one unknown. So I have to know how they are related. And for that reason, I take a time derivative. If you do that, this is going to be V of B. This is a constant, has no time derivative, is equal to, here it is a square root, so it is going to be the derivative of under the square root term with respect to time divided by 2 times the square root. And the derivative of this guy with respect to time, since it's not directly a function of time, you use the chain rule. First take the derivative with respect to delta YA, and that is going to be 2 times this term times the derivative of the interior with respect to YA, which is -1, so we get -2 times 3 minus delta YA. So far, this is the derivative of under the square root term with respect to YA, but now, since it's time derivative, it's going to be multiplied by derivative of YA with respect to t, which is going to be VA. Okay, so this relation here is the relation between VB and VA. Clearly, you see, even the constants of this proportion is not a constant number, right? If you cancel out the two negatives here, right? So let me get rid of the two negatives on both sides. You see that the relation between VB and VA does depend on location of A, right? How much A moves, right? In the beginning, when it has not moved yet, YA is what? Delta YA is 0. You'll see that you'll get a 2 and a 2 here and a 2 and a 3, so it's going to be 3 over 2. So in the beginning, VB is 1.5 times VA, but the system is starting from rest, so both of them are 0, that's okay. But at the end, when delta Y of A is what? 1.33, so if I plug in now this number into this relation, it gives me that in situation 2, when both block moved as I want, block B 1 meter, block A 1.33 meters, V of BA is going to be some number times what? V of AA, correct? And again, you have to plug in the number here, and you will get 0.641 times VA in situation 2. So this here we definitely need when later we go and solve for the work energy equation. And as I always say, it's always a very good practice to number your equations. So this one I will call equation 1, and this one I will call equation 2 because I need both of them. Okay, so far we clearly see the velocities are not the same at each point, their magnitudes. Good. Now let's talk about what happens in the beginning and at the end. In the beginning especially, it says the system is starting from rest and then B goes down. Well, how can that be? When it says starting from rest, does it mean the system starts from equilibrium, static equilibrium? The answer is no. The system initially does not start from equilibrium, because if the system, you let it go, B is heavier than A, B is going to drop, A is going to go up, and then what happens? Well, because B is going down, right, and mg is dominating the tension, then this tension is trying to lift up A and dominates the y component of that tension, tries to dominate the weight of A, so tries to lift up A, and initially it might, until what? Until this spring is stretched enough so that the spring also pulls back, tries to help the gravity of A to counteract the tension component, and then both systems come to rest, right? So your tension is now big enough to cancel weight in B, and the spring force is big enough so that force plus the weight of A cancels the y component of tension on A, so the system goes to equilibrium. But it's a good idea to take a look at some numbers and see right now with this angle alpha, which is arctangent of 2/3, and with the weight and everything, what's going to happen? So first, if I calculate alpha in the beginning, right, alpha in situation 1 is how much? Well, clearly it is tangent inverse of 2/3, right? You clearly see it is in this triangle, and it's 2 and 3, right? So that's what alpha is in the beginning. Now, let's calculate the number. So we use MATLAB, and we use A10D of 2/3, and we'll get 33.69. Good. Now, the weight of B is 135. So this number here, mg of B, is 135 times G. Correct? So let's do that. 135 times 9.81. That's 1324.4. So this is 1324.4 Newton. This is MBG. MAG in the beginning is how much? Let's calculate that one as well. So that one is 90 kilogram. So 882.9. Now the question is, can the difference between these weights with that angle alpha lift up the object A in the beginning? Well, as I told you, in the beginning you have this tension T, and even if I assume this tension is as large as the weight of B, just a little bit smaller, so that B still can move down, right? So T, we consider it very close to this number, a little bit less, so B is still allowed to move down. So let's just use 1324 and keep that 0.4 alone, so B still can go down. So T is like the max it could. So if we consider some very large number, with that T and with the component of T in the vertical direction, which is T cosine of alpha, is this T cosine alpha going to be bigger than 882? So let's find out. Okay, so we are going to use 1334, correct, which is the number that we had here, up here, here, 1324, and then multiplied by cosine of the angle, which is 3369, and you see, yes, it is going to be 1101.6. So you clearly see the vertical component of the T in the beginning can easily dominate weight of A and lift the system up, okay? So yes, the system can allow B to go down, A to go up, and as I said, it goes up until what? Until the spring force is now, because in the beginning, if you assume it's zero, it keeps growing, the spring keeps getting stretched, and that force is going to be bigger and bigger until when this guy goes up. By the way, you know the angle the angle gets bigger. You clearly see here, this is the angle alpha, while in the beginning that was the angle alpha. So since angle alpha gets bigger, the cosine of it gets smaller. So the T component that is lifting up, as it goes up, it drops because alpha gets larger. And the spring force gets bigger, and it's enough that this force plus the spring force balances out with the T cosine alpha, then the system will stop, right? So yes, that's what's happening, okay? That's what's happening. Now, if all of this is happening and the system comes to rest, right, comes to equilibrium, now, if you release it, as the problem says, from the rest, so you release the system from the rest, what's going to happen? Well, nothing, because the system already came to the balance. It already came to equilibrium. Nothing is going to happen. No object is going to move. The forces are already in balance. Nothing is going to move. So the system is not going to move, and of course the velocities are going to be zero all the time. So this is not probably what the problem was thinking, right? What the problem was thinking, the only way that you release the system from rest and the system still moves, B goes down, A goes up, is in the beginning, the system was not at equilibrium. So please pay attention. The fact that you say it's released from rest, it does not imply equilibrium. All it implies is that initially velocity of block A was equal to velocity of block B, and it was 0 meters per second. It doesn't mean the forces were balanced, the velocities were zero. Why? Because initially I kept it in balance artificially. So I apply a force as big as mbg. I applied a force as big as mbg that would cancel the weight of B, so I did not really need any tension in the rope to keep it in balance. Okay, I did not. So what happened to A? How was A in balance? Because of the spring. So the spring, if you look at block A in the beginning, it has the mass down, the mg mass times g down, but it would compress the spring, and the spring will apply what? An upward force, Fs, which would be big enough to cancel its weight, and so the system will be at an artificial equilibrium. Why artificial? Because I have this force F from outside. Now what happens? Then I remove this force. Let's say I hold my hand right here. Right? I hold my hand right here, and then what? I remove the hand. Correct? So this is my hand. And I remove it all of a sudden, and then what happens? Since this force F goes away, the balance is broken. Now B starts to go down, the tension is not going to be zero anymore, and the system starts to move. Okay, so the only way you keep it at rest in the beginning is through some external force like this. Okay, so in the beginning, definitely my spring has to be what? It has to be compressed. Now, how much is the compression? I need that. Because later we want to calculate the work of the spring, I need to know initial and final compressions, or elongations in general. So this is in position 1. In position 1, you clearly see that the spring force has to be equal to MAG for balance. And the spring force, as you know, it is K times S1, where S1 here is the initial elongation, or you can say delta L1, delta L of the spring in position 1. This is equal to MAG. Therefore, the initial elongation, again, S1 is the initial elongation, is MAG divided by K. And here the K is 300. And MAG, I guess we already calculated that. It was here, so we just divide that by 300. And 2.94 is the initial compression. Okay, so this also we need, and we are going to call it relation 3. Okay, so here you see we have 1, 2, and 3. These are all the numbers I need. Now, if I ask you right here, how much is the second elongation of the spring, which is basically when A is gone up 1.33 meters, correct? When A is gone up 1.33 meters, how much is the second elongation in the spring? Initially, it is compressed for 2.94. Now, 1.33 meters of that is released. It moved up. So S2 is S1 minus delta Y of A, correct? Because that amount of it is released. So if you subtract, you get 1.61 meters, correct? This is the final compression in the spring. Now, before we can write our work energy equation, we first need to have our free body diagram to show all of the forces on the system, and then we can proceed. And we also need to establish a coordinate frame. Now here you have 2 blocks, and so you might say, well, I'm going to have 2 separate free body diagrams, one for A, one for B, right? And then if you do that, that's okay. You get 2 equations instead of 1, because you can write work energy for each one. But you're also bringing 1 extra unknown, which is the tension in the rope, because the tension in the rope does a work on each one of these particles, right? That's okay, you can do that. So you have 2 equations with 2 unknowns. One of them is velocity of A or B in situation 2. The other one, as you know, is related. And you also have tension. So you can do that. That's one way. Or you can combine both of these objects into one FBD. And then T is going to be an internal force. And so now we can write the work energy for the entire system. The only question is the sum of the work done by the internal force T on the whole system, is that equal to 0? Because remember, I said something very important in class. I said that while the internal forces themselves can cancel out, right, because they're action and reaction, the work done by the internal forces is not necessarily 0, right? Especially like when you have a friction that is opposing the motion of one object and as well the other object. So the terms of friction, the work of friction, both negative. And when you add those 2 negative terms together, you will never get 0. So that's very, very important to pay attention that the internal forces, when you sum them up, they cancel, but the work of the internal forces does not necessarily cancel. And one example that I said always you have to pay attention is the internal friction, right? So in this case, there is no friction, and even if it was between A and the vertical guide, which is an external to the whole system. So friction is not to worry about, it's just the tension in the rope. If I combine FBDs, would I be able to say the work of tension on block B and A, sum of it is equal to 0? The answer is yes, but it needs some mathematical derivation, and I'll show you why that's the case. So in this case, instead of 2 FBDs, I'm gonna just draw one for the entire system. So here is block A, this is block B, and I would include the pulley as a part of the system as well. Okay, so this is my system. Now what are the forces on it? Well, clearly the mg terms. That's the first thing that you should always include, unless they say mass is negligible. Then what? Now tension is an internal force. We neglect the work of it here. I'll show you why. The other thing you have is the spring. The spring was initially under compression, and it is finally also under compression. It's all the time under compression. So the spring force in this case is going to be upward like this. Then you have the reactions at the pulley. Let's assume that there is no friction at the pulley, no viscous friction or anything. You have a contact between block A and the vertical shaft, and that would mean you have a normal force and a friction, but the friction is negligible. It says neglected. So this is my FBD, and I'm going to use the traditional X, Y, and Z coordinate system like this. Okay, so again, I neglected T, and I'll show you why, but this will help me just go with one FBD instead of 2 and not solve for the unknown T, which is not of interest in this problem. So now I can say that the total work in this system between the two positions is equal to, now which one of these forces is doing any work? OX and OY clearly do not do any work because they are applied to the stationary point O, the center of the pulley, which does not move. N is perpendicular to the direction of motion of block A. Block A clearly it is going up, and block B is going down. So N, which is perpendicular to the direction of motion, doesn't do any work. So all that I have for doing work is the work done by the two mg's as well as the spring force. Correct? And this is equal to K2, the total kinetic energy in position 2, minus K1, the total kinetic energy in position 1. Okay, so this is my work energy equation for the entire system. Now, in the beginning, both objects have 0 speed or velocity magnitude, so K1 is clearly 0. K2, it is going to be sum of the two kinetic energies. In this case, we cannot combine the masses and say it's 1/2 of the total mass times the common velocity squared, because there is no common velocity. Each block has its own velocity. So you have to add the individuals. You cannot factor out V and add the masses together to get K2, right? And the work by the mg's, you know, we learned in class the work of mg on a particle. In general, it is negative mg times delta y of the object. And we learned that the work of the spring in general is what? Negative k over 2, where k is the constant of the spring. times S2 squared minus S1 squared, where S here is the elongation, right? And as I told you, in this case, K is going to be 1/2 of the mass of each block times the velocity of the block, in that situation squared. Okay, seems like I need to keep shifting this FBD further and further to the right. Okay. Right, so these are all the terms that I have, and now if we plug in the numbers, so it's negative 90 times 9.81. Block A goes up by positive 1.33 meters. Negative MB times G. Block B goes down, and remember I told you that delta Y has sign. When it goes down and Y is upward, it means it's -1. The spring force is 300, K is 300, S2, we calculated it, it is 1.61 squared. Initial one is 2.94. It's equal to 1/2 mass of A times velocity of A in position 2 squared plus 1/2 mass of B. Now here, instead of velocity of B in position 2 squared, I'm going to bring in the relation that I had in equation 2. So here I need to use equation 2, and it is going to be 0.641 times velocity of A in position 2. That is V of B in position 2, this whole thing squared, right? Therefore, from here, I can clearly see I only have one equation with one unknown, V of A in position 2, and if I solve for that, I am going to get 3.82 meters per second, and if I plug it back into equation 2, that gives me V of B in location 2, that will be 2.45 meters per second. Okay, so these are my final answers for each block. And now, as I said, there was one thing that I needed to show you, and that is the work of T on the two blocks. When you add it up together, it will be 0, right? So you can neglect the work done by the internal force T. Why is that the case? Well, let me show you. So this is block A, this is T, this is angle alpha, right? And this is block B, this is T. Now, if I look at this here, this triangle for arbitrary location of A, if you remember, the sides are 2 and then 3 minus what? Y of A. So if I ask you, what is angle alpha at arbitrary position, you say alpha is tangent inverse of basically 2 over 3 minus delta Y of A. Correct? And if I also ask you what is cosine of alpha, because that's what we need, really, cosine of alpha, you say it is the adjacent, which is 3 minus delta Y of A, divided by the square root. Correct? So that is cosine of alpha. If you don't mind, I will call it relation 5, because that's what I actually need, 5. So when this object A goes up, we have to calculate work of T. You know, you have to multiply T by alpha, right? This is the component that you calculate the work of it, T cosine alpha. So here, I'm going to calculate the work of A as it just goes a very small distance up, dya. And B, when it goes down a small distance, dyb. Clearly, you know, dya and dyb are not the same number, but they are related. We need to go back to the equation that involved the velocities of A and B, which is this general equation here, up here. So you know V of B is dy, V of B is dy of B over dt, and V of A is dy of A over dt. So if I multiply both sides by a dt, I clearly can find dyb related to dya. If I cancel out these 2's, you will get this relation. Now, if I ask you, what is this coefficient here? You say, if I go back and look at equation 5 that you just derived, that is cosine of alpha, right? So clearly, I can say that dyb is equal to cosine of alpha at any point times dya. This is extremely important. I call it 6. So now, if I go and calculate the total work of T in this system between position 1 and 2, you say it is equal to the work of T on B. B is going down, T is upward, the angle is 180, so it is negative T times dy of B. By the way, it's really, you should not write it as total work, you should write it as dW because your displacement is infinitesimal. So negative T dy of B is the work of T on B. Work on A is positive T cosine of alpha times dy of A. Because A is going up, T is upward, so the work is positive and is related by cosine of alpha. And now, if you plug in the relation 6, which says y of B is cosine alpha times dy of A, clearly you see the sum of it is 0. So in each infinitesimal displacement of the system, T does not do a total work. And so, of course, when you integrate that, the total work of the T between the two positions, which is integral of this, right? You're integrating 0, so you'll get 0. Right? So you clearly see why tension does not do any work. Right? That's why I could neglect it here and say that the work done by this internal force T can be considered as 0. And then I solve for my two unknowns. Okay, so when you solve a problem, you have to have all of these discussions. Why you can neglect the work done by an internal force like T if you are not using two separate FBDs, and why the system is initially at rest, although it is not in a static equilibrium, because if it was, it wouldn't move any further, right? You have to discuss all of them. What is the initial compression in the spring and so on. Then you can solve for the unknowns. So hopefully it was useful to you. I'll see you in the next example solved.